Hi, sorry. Okay, so what could happen? When does f of x have no slope? I want you guys to think about this. Like, what could happen for there to just not be a slope? Infinity, Canna. That's actually really interesting, and that is one of the answers. So, like, this infinity could happen. So asymptote, yeah.
It could also be like when it's empty point, so like it doesn't exist, like
So
the function
you
doesn't
got
exist.
it. So like an asymptote could happen when
Yeah.
when there's like that empty point, it doesn't exist. What have we in this class learned to call those two things? And there's a third one of them as well.
Discontinuity.
Continuity.
Discontinuities, exactly. So that's going to be the first place where the function has no slope, if there is a discontinuity. So a good way to think about that is if the function, well, actually, we'll just look at pictures. That's a better way. So discontinuities. Actually, we'll do this like this. And this is going to be the first time it happens. So when I have a discontinuity, actually, I don't. And we have 3 different types of discontinuities. You guys brought up 2 of them, so we're going to start by looking at those 2. So the first one that you guys told me about was an infinite discontinuity. You guys were talking about asymptotes. So that might look something like this. With how I have drawn this, is f of a defined?
No.
No. And if it's not defined, if there's no point, is there a place for me to draw my tangent line?
No.
Nope. So that's one possibility of what could happen here. Either f of a is not defined, and therefore there is no place for me to draw the tangent line. Or is f of a defined now?
Yeah.
Yep.
But there's no like slope. It's just a dot.
You got it. Exactly. There's no slope. There's just a dot. When we draw a tangent line, so I'll remind you, the tangent line touches the curve at one point. It just grazes the curve at one point and is parallel to the curve. So we're using the curve on the left and right side of the point to kind of figure out what the slope looks like. If I were to draw a tangent line here, maybe it would look like that, or maybe it would look like that, or maybe it would look like that. It's not connected to the function for me to be able to figure out what the slope is, right? There's no function that shows me what direction that line should be going. There's no slope, it's just a point. Okay, so then you guys talked about removable discontinuities. We actually have exactly the same thing going on here. With how I've drawn it, is f of a defined? No, if I were to draw my tangent line, sure, I've got graph to the left and right. Oops. Hang on. Sure, I've got graph to the left and right. Is that tangent line I drew actually touching my function?
No.
It's just touching the hole. It's just touching that hole I have there. It's not actually touching the function. And if I were to define it, would I have the same problem that I had over there at infinity, where I have that line kind of going every, that could potentially have any slope?
Yeah, same thing. There's no slope, so you can't draw a line.
Same thing, no slope, can't draw a line. Same issue. Okay, take a second, make sure that you guys are with me with this. Any questions about this? What's the third kind of discontinuity that you guys haven't mentioned yet?
Hold discontinuity or removable.
That's the one we just did.
Oh, no, sorry, jump. Yeah, interesting. Yeah.
Jump discontinuity, which would look something like this. I'm going to define it right there. Actually, let's make that prettier. So this is my jump discontinuity. I kind of have the same issue here, but I could also think about this in a little bit of a different way. If I use the curve on the right side to draw a tangent line, and I try to follow that curve from the right side, my tangent line might look something like that. So if use curve on the right. If I use the curve on the left to draw my tangent line, it's going to look something like that. Do those lines have the same slope?
No.
Nope. So we kind of have the same problem here. It's only defined on one side, or it's not defined at all. But also, if we use the left side of the curve versus the right side of the curve, we're going to end up with a different slope. So we have the slope from the left not equaling the slope from the right. So we saw that derivative is a limit. Derivative is an expectation. Our expected slope on the left is different than our expected slope on the right. Okay, so in other words, what we're seeing is that if there is a discontinuity, then I don't have slope, and therefore I do not have a derivative. So another way of stating that is by saying that if f of x is differentiable, then it's also continuous. So if it's differentiable, then it's continuous. Or I could restate this: if f of x is not continuous at x equals a, then f of x is not differentiable at x equals a. So how I've stated this is actually really important. If it's differentiable, then it's continuous. If it's not continuous, okay, I wrote that backwards, my bad. Yeah, if it's not continuous, then it's not differentiable. But this doesn't mean that there are places where it could be both continuous and differentiable. So in other words, not being continuous means that it's not differentiable. But being continuous does not mean that it is differentiable. So that's a little bit hard to wrap your mind around with just words. So we're going to create a second section here. The second different place will be continuous but not differentiable. And people tend to have trouble with this because it really is largely a thing that you learn in a logic class. Understanding that these two phrases are not telling me that not continuous, or rather that continuous means differentiable. So it could be continuous but not differentiable. And there are two types of places that this could happen. Are you guys caught up with me?
I am.
Awesome. Okay, so the first thing that could happen is something that's called a corner. And a corner looks something like this. So when you look at this function right here, is this continuous at x equals a?
Yes.
Yes. Do I have to pick up my pen to draw it? Don't. It's continuous. So this is continuous at x equals a. But kind of like the issue that we had with the jump discontinuity. If I were to go to A and try to draw a tangent line, and I use the curve on the right to guide me in drawing that tangent line would look something like that. Whereas if I use the curve on the left side to guide me, am I going to end up with the same slope?
No. Well, just reversed. Like.
It's not just reversed. It could be if they were really just like perpendicular.
Yeah.
But yeah, so it's going to be actually going in a different direction even. If I try to draw it this way, that would be my left tangent line. And they're not the same. So what I have here is a really abrupt change in slope. I have it going boom and then suddenly starting off just abruptly in another direction. So using the left side versus the right side to guide me will give me a different value. So here I don't have a derivative because, again, I stress a derivative. Was a derivative a limit?
Well, it's like a limit as h approaches 0. So.
Right, so a derivative is a limit.
Yeah.
And it's a limit that represents slope. And limits, I remind you, are expectations. My left expectation here gives me one slope, and my right expectation gives me another slope.
So it's like a lim when it's minus and plus, and when they're not the same, it's DNE.
Exactly, exactly. So here this wouldn't exist because on the left side and the right side, it's two different things. So it's kind of like a jump discontinuity, but for differentiability. So here the derivative doesn't exist because the left expectation does not equal to the right expectation. So this could show up, this same issue could show up in another way called a cusp. And cusps and corners are pretty much the same thing. They just have a little itsy bitsy difference. A corner is when it's like boom, boom. A cusp is when it kind of like slowly moves into the point and then jumps out. So a cusp could look something like that. So where you actually have curve instead of just like straight line going in. And it has the same issue if I use the left side to guide my tangent line versus the right side to guide my tangent line, I have a different slope. So cusps, corners, another way of talking about them is by saying they are an abrupt change in slope. Are there any questions about these cusps or corners? So that's my first way. So then there's another place where the function could be continuous but not differentiable. And in order to understand this one, we need to do just like a brief review of slopes. If I have a horizontal line, what's the slope of a horizontal line?
1? Or no?
A.
Let me draw it.
X. 0.
Yeah, it's 0. So let's just think about why. So we're gonna do like a mini review here. Mini review before I write it down. If I have a horizontal line, so that's like y is equal to a. Remember that slope is equal to change in y over change in x, right? What's the change in y here?
0.
You got it. There is no change in y. So this is equal, actually do this. This is equal to 0. There is no change in y. So x is this, so we have x changing. If I have like x2 minus x1, if I pick some points, like these 2 points right here, x2 minus x1, I'm gonna get a value. But y2 minus y1, the y values are the same. There is no change in y. Does that make sense? And guys, I know it's a mini review, but like horizontal tangent lines are gonna be important really shortly. So that said, what if there's no change in x? What's the slope if there's no change in x?
Division by 0.
Division by 0. What kind of line might give us no change in x?
It'd be a vertical line, no?
You got it, a vertical line. So that horizontal line gave me no change in y. So this is a horizontal line. So if I have a vertical line, my vertical line might look something like this, and it's going to be x is equal to a. Oops. X is equal to a, and the same thing, if I have 2 points, well, I only have one x value. So no matter what, even if I have like 2 different y values, there's a change in y there, but it's always the same x value. So there is no change in x. So here the slope is still change in y over change in x, which is going to be change in y over 0. What does division, a constant divided by 0, cause?
Infinity.
Infinity, you got it. So in this case, we actually say that vertical lines have infinite slope, which really is like saying they have no slope. Okay, mini review over. Are there questions about horizontal or vertical lines and their slopes before we use them to talk about derivatives?
I have one question.
Yeah, what's up?
Wouldn't the vertical line not be considered a function because it doesn't pass the vertical line check?
It would, and that's why we're gonna have to like really, so it's not a function. Definitely
Okay.
not a function. But we're gonna see how something like this could still show up in a function to cause a problem. Okay, so that said, no vertical lines aren't functions. But what if something had a vertical tangent line? And that is our second issue that we could have, a vertical tangent line. And a vertical tangent line is going to look something like this, where on its way down, it just really briefly goes straight for just one itsy bitsy second. So a lot of times when you're looking at a function, vertical tangent lines are hard to see because it's like this. It's like, boom, except it does it so fast because we know that if it stays vertical for more than 1 point, it's no longer a function. So it really is vertical for just 1 point right there, which is why oftentimes you'll see a dotted line to show you that the tangent line there is vertical. Does that dotted line mean this has a vertical asymptote? No, right? A vertical asymptote would be specifically going up to infinity. It's not doing that. It's just telling me if I draw a tangent line right there, the tangent line is vertical. The function is vertical for just a second. So the tangent line is vertical. Be careful. This is not a vertical asymptote. And guess what? That's it. These are the only places that a function might not be differentiable. So a function is not differentiable places where a function is not differentiable. One, we said discontinuities. Two, we said cusps or corners. And then 2b, the thing that we just saw, are vertical tangent lines. Again. So the first question will be, list all of the x values where f of x is not differentiable. And so for these questions, especially because a lot of times we're asked afterwards to separate the different types of non-differentiability, it makes sense if you're asked this to separate this into the 3 different things that could happen. So we're going to start off by listing the discontinuities. Hopefully you guys are still good at that. So starting from left, let's move from left to right. What's the first x value where I have a discontinuity?
-2.
X equals -2, you got it. What kind of discontinuity do I have there?
Infinite.
Infinite, good. So someone else now, what's the next x value where I have a discontinuity?
-1.
Minus-
Actually, yeah,
Yeah, -1, you got it. And what kind of discontinuity do I have there?
jump.
A jump, yeah. So x equals to -1. I'm not writing the types because I wasn't specifically asked. What is the next discontinuity? Someone else.
That's 2.
It's at 2, you got it. And what kind is that?
Removable.
Removable. So we had all 3 different types of discontinuity. We listed them. Next, I'm going to have a little section for our cusps or corners. So again, let's move from left to right. Remember, cusps corners are like super abrupt changes in slope. Where do those happen?
X equals 7 and 8.
So 7 and 8 are 2 of them, but there's actually one more.
4.
4, you got it. So -3 doesn't have an abrupt slant change in slope, but that is one that we're going to look at in a second. So that 4 right there, it looks a little bit different. If I draw above, it's like, I put it in red so that it was really clear, but it's like that, right? So that is a place where I have a super abrupt change in slope. Looking at the left and right would give me something different. So this is x is equal to 4, 7, and 8, where 7 and 8 are the really obvious ones.
For an exam, like, because here we're doing cusp/corners. For an exam, if you're asked to list them, would you have to specify if it's a cusp or corner?
No, I'm not going to ask you to separate those.
Okay.
That said, 4 is a cusp and 7 and 8 are corners. Nope, 8's a cusp, I'm sorry. Okay, so then we also have vertical tangent lines. And that's what Kiana said. That vertical tangent line, where does it happen?
-3.
At -3, exactly. So that's the -3 that Kiana mentioned before. That -3 is our vertical tangent line. X is equal to -3. Are there any other places where this function might not be differentiable? Nope, that's it. Right, those are the only 3 places. We have our discontinuities, and then we have the others. So then the second question you might be asked is, list the x values where f of x is continuous, but not differentiable.
Wouldn't that all be the cusp, corners, and vertical tangent lines?
You got it. We've already listed them. And so that's one of the reasons that if you're asked that, it's really useful to separate them, because usually you're then also asked this question, but not differentiable. And so if you're also asked this question, you don't have to redo any work. You don't have to think about it. You already have the answers. That's going to be the cusps and corners and the vertical tangent line. So this is where it's continuous. So here I can just immediately go x is equal to -3, 4, 7, 8, where that's my vertical tangent line. And those are my cusps and corners. Okay, are there any questions about these two questions that we've asked about the graph? Okay, so then the next question is, what other things can I know about a derivative just by looking at a graph? So my third question will be, is f prime of x positive or negative at x equals 1? So remember, f prime, that's our notation for derivative. So this is another way of asking this question, is saying, is the slope positive or negative? But specifically, the slope of the tangent line
At x equals 1?
at x equals 1.
Wouldn't that be positive because the function is positive?
You got it. Well, not because the function is positive. So the function being positive isn't
Oh,
really.
yeah, sorry.
Yeah.
It's just at that point, the line is going up. So.
Exactly. So if I were to draw a dot right there and draw my tangent line is going to look something like that. So the tangent line looks like that. The tangent line has positive slope. So the answer here is positive. So now I'm going to ask you about another x value, and I want the answer to be negative. What x value could I ask you about that would give you a negative slope?
Anything
5.
after?
Wait, what was that?
Like 5.
5. If I ask you about 5, that's going to give you a negative slope. You got it. Anyone else? So David, where were you going to say?
Anything after 8?
Anything after 8? Are there any other places that will give you a negative slope?
Well, towards infinity, between -1 and -2.
Yeah, so between -1 and -2. So there are lots of x values that I could ask you about. Do you guys see how we can just look at the shape and find a tangent line? So I'm going to ask you about, like, let's say 9. If I ask you about 9, so we go up here and we're like, that's 9. I draw my tangent line. That clearly has a negative slope. So my tangent line looks something like that. Tangent line has negative slope. So that's one thing. I can figure out if the derivative is positive or negative. So to really just like clarify, what this is saying is that f prime of 1 is positive. And this is saying that f prime of 9 is less than 0. Does that make sense? Because the slope of the tangent line tells me the sign of the derivative. Okay, so if the slope of the tangent line tells me the sign of the derivative, the next question I might ask you would be to list the x values of the horizontal tangent lines.
Is that x is equal to -3?
X equals what?
-3?
Not -3, that's a vertical tangent line.
Oh, okay.
-4.
-4 is going to be a horizontal tangent line. Do you guys see any others? Remember, a horizontal line looks like that. Where might I draw a tangent line and end up with a horizontal line?
Could
Maybe
4
at
be
0?
one?
X is equal to 0?
0. 0 is going to be a place. So not 4, Kiana, but I think you're maybe thinking the right thing. There's one other place that it's going to happen.
Oh no, 8.
At 8, we already said what's happening at 8 is that we have a corner. So that's not going to be horizontal. That's just not going to be.
X approaches infinity? No?
So right now we have -4 and 0. Where's the third place where I could draw a tangent line and have it be horizontal? Yeah, exactly, Luca, 3. So horizontal tangent lines can appear in 3 different ways. They usually occur when I have humps like that. So if I have a hump, then at the top of that hump, I'm going to have a horizontal line. And at the bottom, I'm going to have a horizontal line. Or they could occur at places like with what's happening at -4 there, that are similar to vertical tangent lines where it just goes straight for just a second. It would be a question, Xavier, and we would answer it a little bit differently. I'm actually going to ask that specific question in just a second. So these are the 3 different ways. Yeah, Lucas, 3. That I'm going to have my horizontal tangent lines. So one is at 3, one is at 0, and I don't know why I'm trying to use my mouse to do this. One is at 3, one is at 0, and one is at -4. So if I go back here, I'm like, look at that. There's a horizontal tangent line. There's a horizontal tangent line. There's a horizontal tangent line. So x equals -4, 0, and 3. So these are the 3 different ways horizontal tangent lines might occur. Okay, are there any questions about these horizontal tangent lines? That brings us to the last question I'm going to ask you about this graph, except it's going to have lots of separate parts. What is f prime of 3?
Infinity.
Not -3.
Oh,
It doesn't exist? Because it's a removable, no?
+3 was +3.
Oh, okay, sorry.
Did +3 occur in question 4? Say, someone said it, huh?
2?
Yeah, 0.
Oh, not 2.
Oh,
0.
0.
all right, because of the thing, yeah.
Because of number 4. So we said we have a horizontal tangent line at 3. And what's the slope of a horizontal line? We had our mini review a minute ago.
0.
0. So f prime of 3 is equal to 0. And this is because the tangent line is horizontal and a horizontal line has slope 0. Okay, so now we're going to ask the question that Xavier asked a question ago, f prime of -3.
That would be infinity? I don't know.
So that is tempting, and so that's what Xavier said as well. And it is tempting to put that because we know that vertical slopes have, or vertical lines have infinite slope. Except that what we've said is that in that case, because of that infinite slope, we state that the function is not differentiable. Is -3 one of the things that we listed in number 1?
Yeah.
Yeah, that's our vertical tangent line. So what that means is it's not differentiable. And remember, not differentiable means has no derivative. So when we actually did our little review up here, we said it's infinite slope, or we say that it has no slope. So because of that infinite slope, that no slope, we say in this case that f prime of 3 does not exist. So we don't actually write infinity, we just write that it doesn't exist. And this is because of the vertical tangent line. Line f of x is not differentiable at x equals -3. And I just realized I forgot my negative inside there. Sorry about that. F of -3 does not exist. Okay, are there questions about that? Excuse me. Okay, so do you have a question?
No, I was
No, I
going to
just
say
have
blessing.
one.
Here. So there is another place that we could also ask about. What if I were to ask you for f prime of 7.5? So we're looking at 7.5.
Could you go back, please? Thank
Yeah. When we look at the graph, what type of shape do we have at 7.5?
What do you mean shape? Like,
Is it a
like a-
parabola? Is it a circle?
Yeah.
Is it a straight line?
it's a straight line.
It's a straight line.
Yeah.
What do I need in order to find the slope of a straight line?
Just one x value?
Points.
Points. How many points do I need?
2.
Two.
Well, like, yeah, for like y2 minus y1 or delta y over.
Yeah, exactly. So I'm going to need my 2 points to have a y2 and a y1 and an x2 and an x1. Do I have 2 points on that line between 7 and 8? Can I clearly find out what 2 points on that line are?
Yeah.
Good. So in the chat, privately again, I want you guys to tell me what are 2 points on the line between 7 and 8?
Uh,
That's one of them. Yeah, good job. All right. Yes. Yeah. Almost, Lucas. And also almost, Marine. You have one small problem with yours. So, yeah. All right. Good job. Not okay. So between 7 and 8, f of x is just a straight line. Is just a straight line. So what that means is the derivative will be the slope of that line. So we can find 2 points. And you guys told me those 2 points are 7, 0, and 8, 3. So a lot of you said 8, 2, and it could just be that it was like maybe you drew it a little differently, but that 8 is up at 3 there. So 7, 0, and 8, 3, and then find the slope. So my slope is change in y over change in x, which is 3 minus 0 over 8 minus 7, which is just 3. So f prime of 7.5 is equal to 3. Okay. Are there any questions about how we were able to find that f prime is equal to 3? What other point on the graph could I ask you about where you would find the derivative in the same way?
5.
5. 5 is another great point where that could happen. We also have between 4 and 7 a straight line. So I could also ask you, for example, about 5. Could I ask you about 6?
Yeah,
What would the answer be if I asked you about 7, though?
it wouldn't exist. There's no.
Does not exist. 7 is one of the things that showed up in question 1. That's a cusp or a corner. There is no derivative. Same with 4. 4 showed up there. But I could ask you about 5. I could ask you about 6. Could I even ask you about like 6.9?
Yeah, anything between 4 and 7.
Anything between 4 and 5 and anything between 7 and 8. So why don't we do that? Why don't we ask you about f of 5? F prime. What is f prime of 5? So first we find our 2 points. What are 2 points?
Is 5 and 1 a point or no?
So 5 and 1 is a little bit not exact. That 5 is not supposed to be at 1. And 4 is supposed to be at 1. It's probably just a little confusing with how it's drawn.
Okay.
So, but yeah, so that 4, 1 would be a point. And what would the other point be?
6.5 maybe? I don't know. I can't really.
Well, what's
tell.
another point that we definitely 100?
Oh, 7-0, 7-0. Yeah.
7, 0, you got it. So we have 4, 1 and 7, 0. And so then we want to find the slope. So I say change in y over change in x. That's 0 minus 1 over 7 minus 4, which gives me a negative 1/3, which tells me that my derivative is therefore negative 1/3. Oops. F prime of 5 is equal to negative 1/3. Okay, so I want you to look at question 5. In question 5, I was asking you to find the derivative of things, to find the actual specific derivative. And sometimes the answer was 0, sometimes it was does not exist, and sometimes it was a number. What are the different cases where I was able to ask you that? So I want to elaborate on this question for just a second before you answer. For example, if I were to ask you for f prime of 9, would you be able to answer?
Yeah.
Would you?
Well, if we got 2 points, yeah.
But at 9, is that a straight line?
No.
The curve is, so are we going to be able to get 2 points?
No.
No, I only have 1 point on that tangent line. So with only the information I have here, am I going to be able to find the slope at 9?
No.
No. I don't have a function, so I can't use the limit definition. It's not a straight line. So f prime of 9 is not a thing I could ask you about. It's not something that's going to show up down here. So what are the 3 different types of things that could show up here based on the different questions I've asked you?
Does it need to be like a line, a point, and like be like a definite point or no?
So a straight line, that's for sure. We need a straight line that clearly has 2 points on it. So that's like 7.5 and 5. What about the other 2?
Like an x value, they'll give you a horizontal line, like
Horizontal tangent line, so that's the second thing.
something that'll not exist.
Something that will not exist.
Yeah.
There you go. So question 5, I could ask you specifically for a derivative in 3 different cases.
But the derivative, like, it's not really a derivative if it doesn't exist. Like f prime minus 3.
Right, except I could say, what is f prime minus 3? And you would
Yeah,
tell me
okay.
does not
Yeah.
exist.
Right. But
Right,
it's
you
not
would say there isn't a derivative there.
Okay.
So the first case was we had a horizontal tangent line. So f prime of A is equal to 0. The second case is f not differentiable. So in other words, I have a discontinuity.
But isn't that only for vertical lines?
Nope, it's for
Okay.
any of them. And so that's what I was saying a minute ago as well. And I think you even answered the question. What if I were to ask you about 7? What's f prime of 7?
It doesn't exist.
Doesn't exist, right? So it's not just for vertical tangent lines, it's for all of the places where there is no derivative. The answer is just going to be doesn't exist. So discontinuity, a cusp or a corner, or a vertical tangent line. And so in this case, f prime of A does not exist. And then the third case is the last thing we did. Function is a straight line. So we find 2 points. And f prime of A is equal to the slope. Which is equal to change in y over change in x. And those are really the only 3 cases in which I could ask you this question. So if I'm saying, what is f prime of blah, 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 you should be thinking about these 3 things. That's it. That is all I have to say today. So unless you guys have questions, I am done.
So next class Thursday